First of all, I would like to acknowledge my co-authors given here. This is outline of my presentation. In this paper, I would like to talk about 3 types of low-level jet during the May season over Taiwan. And I would like to talk about those 3 types of low-level jets and how they affect heavy rainfall over Taiwan. There are 3 types of low-level jet. The first is subsynoptic low-level jet associated with Mei-Yu frontal cyclone. The second is marine boundary layer jet below 900 millibars, embedded with a southerly monsoon flow over the northern South China Sea. The third type of low-level jet is orographic and hence strong winds of the northwestern Taiwan coast. And this is an example of jet front system, and this is very typical. First, I would like to show the vorticity maxima. So you see this sloping frontal surface. So this is south, this is north. And you see that warm moist air is being lifted by rising motion ahead of the frontal zone. And here you got a secondary circulation. So axial shower wind, and here you have rising motion, and here in upper level, you have upper level jet. And in this diagram, you can see the cold pool, cold air behind the cold front. And upper level, you see upper level front. Okay. And here, axial shower wind pointing to the main frontal zone. That's where you got subsynoptic low-level jet. So this is the schematic diagram showing the secondary circulation associated with the jet front system. You got upper level jet, you have upper level front and tropopause folding, and you have axial shower wind pointing to May trough, and here you got low subsynoptic low-level jet. And this is barochenic system, and this is barochenic conversion associated with the Mei-Yu frontal cycle. If we don't include latent heat release in the model, this is with a latent heat release. So latent heat release is quite important for barochenic conversion. So this is summary. All Mei-Yu fronts are driven by a moist barochenic process, and latent heat release is being enhanced. The barochenic conversion is enhanced by latent heat release. And LLJ is caused by the Korea force acting on the lower branch of the secondary circulation across the frontal system, with a wind maximum between 700 and 900 millibar layer, and rising motion associated with the secondary circulation brings the warm moist air vertically upward. This is one example of the Mei-Yu frontal zone. And in this case, I would like to introduce marine boundary layer jet. So you see warm moist air being lifted above the frontal zone. And you got rising motion along the leading edge of the cold front. And to the south, you see moisture transport below 850 millibars by the marine boundary layer jet. And we identified 21 days with marine boundary layer jet during 2008 and 2012 in June. Okay, those are the days. And we identify marine boundary layer jet based on vertical wind profile, wind shear, and also the wind speed. And this is a composite 925 millibar winds. You can see the jet core right here. And this is a transient features because I don't see this in a mean flow. So the main reason for the marine boundary layer jet is due to deeper frontal Mei-Yu front and also stronger subtropical high give rise to larger pressure gradient. And how come the maxima is at 955 millibars? because this is due to frictional force in the marine boundary layer. So to show that, you can see the wind profile associated with the other jet core or the marine boundary layer jet. You can see the Ackermann solution, Ackermann spiral. And at 900 millibar, the flow is super geostrophic. So this is geostrophic wind. So you have a geostrophic wind pointing toward lower pressure. And this is composite showing the frontal structure and also this is equivalent potential temperature. So high equivalent potential temperature air is below 850s and being affected vertical upward by the secondary circulation associated with the subsynodic scale low level jet. And in the meantime, you have moisture transport by the marine boundary layer jet to the frontal zone. And how does that affect rainfall? So this is the rainfall distribution for the marine boundary layer jet days. This is June mean, and this is the ratio. So the southwestern Taiwan being enhanced with higher precipitation under marine boundary layer jet days. And this is a schematic diagram showing the marine boundary layer jet being lifted due to blocking and lifting and also rain evaporative cooling. The third type of low level jet is the localized barrel jet over northwestern Taiwan, just showing here. This is observed by aircraft data. And you can tell you have flow splitting and you have flow acceleration down the pressure ridge that is orographic induced. And on a large scale pattern, you see this Mei-Yu trough, and you got southwest flow impinge over the island of Taiwan. And this is the vertical profile of the barrel jet at a maximum of 1 kilometer. So this is top of the mix there. So this virtual potential profile below it is well mixed. So this is due to friction reduction of the wind speed. This is the schematic diagram of the marine boundary layer jet and the barrel jet. So this is Mei-Yu trough, this southwest flow, and then that gives rise to strong winds due to orographic blocking. And this model simulation, and you can see the flow splitting right here, consistent with observation, and you have pressure ridge due to orographic lifting here and blocking, and the wind accelerate downstream. That is Lagrangian flow, acceleration of the northern branch of the deflected airflow along the coast due to pressure gradient force. Okay. The barrel jet also enhanced horizontal moisture transport. How does that affect the convection? The keywords is low level convergence. The enhanced convergence along the wind shift associated with frontal zone. So this is convergence being enhanced by barrel jet. And the initial stage, this is well-developed stage and later stage and propagate along the rain band. So this is back building based on a case study during IOP 13 of TMX. This is another case, and this is prefrontal. So you have barrel jet converge with southwest flow, and the flow is modified by convection and rain evaporative cooling. So one of the important findings of TMX is due to the role of localized convergence between barrel jet and frontal wind shift line or the southwest flow that caused the localized convergence and heavy rainfall over northwestern Taiwan. And we have several cases, and additional cases are reported during TMREX. Could all three types of jet coexist? The answer is yes. This is the vertical cross-section for the composite field for the marine bounded layer jet base. So you can see marine bounded layer jet right here. This is south, this northeast, and here you have sub-synoptic loader jet, and here you have barrel jet. In here you have upper level jet. Okay. So the marine bounded layer jet brings the moisture from the south. And the secondary circulation associated with the jet front system provides the large-scale lifting. And the orographic and local effects provide localized conversion and lifting for heavy rainfall occurrence. So this is my my summary. Thank you for your attention.